Welcome. So this is going to be our lecture on starting on kinematics, which we have up here. Kinematics right here. And what kinematics is kinematics is, I've defined it for you right here. Kinematics is the study of motion. So to study anything, any object's motion, we need to understand its position. So its position is where an object is at any particular time. That is an object's position. You must know its position relative to its frame of reference, which we have talked about in the past. Usually that frame of reference for us is the Earth. If an object moves relative to its frame of reference, then its position has changed. And when a change in position occurs, that's what we call a displacement. A displacement. The word displacement implies that an object has moved. So down here we have an example. We have a beaker of water. This is H2O, water. And we take that beaker and we take it from this position here to this position here. And that is our final position. So we have displaced the beaker of water. Continuing. Calculating displacement. So we can calculate displacement using the following equation. And that equation is right here. So we have delta x, which is displacement, and we have x of f, which is the final position, and we have x0, or the initial position. So to calculate displacement, we take our final position and we subtract our initial position, and that will give us displacement. So here we have our beaker of water again, and let's go ahead and take our beaker of water, and we have its initial position is 1.5 meters and its final position is 3.5 meters. So what is the glass of water's total displacement? And be sure to give your answer with the proper amount of significant figures, which was our last lecture, and a proper label. So go ahead and answer that question now. So keep in mind that when we are using our coordinate system, we can have a negative displacement as well. So now in this example, our x initial of the water is 6 meters, and sorry, that's an ugly O. Redo that, H2O, there, that's better. Our initial position is 6 meters, and the water's final position, XF, is 2 meters. Then what is our beaker of water's displacement? So let's revisit velocity. We've talked about velocity in the past, and I just want to clarify our equation for velocity because we're going to be talking a lot about it. So I gave you this equation. Velocity is distance divided by time, or v equals d over t. I simplified this equation, and I simplified it a little too much, so it's important to know that I had simplified the expression of the equation. Now that we know about displacement, let's dig in deeper to this equation. And this is our equation down here that we will use going forward to calculate velocity. So this equation establishes the relationship between displacement and time. This is also how we calculate average velocity. So average velocity, as indicated by this this bar right over the V here, that indicates that this is an average velocity. And you can see that we've taken delta x, which is our change in displacement, or is delta x is displacement, and we've put it over delta t, which is a change in time. So it's a change in position over a change in time, or x of f minus x0 divided by tf minus t0. So xf is our final position, same as it was in the displacement. x0 is our initial position. And correspondingly, TF is our time when at our final position. Final position. TF is our time at the final position, and T sub 0 is our time at our initial position. All right, so average velocity. What does average velocity mean? We said that our symbol, our V with a bar over it, is an average velocity. So an average velocity does not, in fact, tell us much about an object's motion. A lot can happen between the starting point and the finishing point. For example, if the arrows below in our diagram here, so our diagram down here, our airplane, indicate a passenger's movement in this airplane, we can see that there was a lot of movement by this passenger. So the passenger went from the front of the airplane, a little bit back, took a little break, moved again towards the back of the aircraft, then he moved forward in the aircraft, then they again moved towards the back of the aircraft, and that, if we calculated our average velocity, we would say it took the passenger 5 seconds to move -4 meters. The passenger's average velocity would be -0.8 meters per second. However, as we can see in this diagram, the passenger had several intervals of different movements. So average velocity doesn't always tell us everything there is to know about an object's motion. Instantaneous velocity, however, is when we make the intervals even smaller and smaller when considering the motion of an object. The more detailed information we can extrapolate with instantaneous velocity. If we keep making the intervals smaller and smaller, they become infinitesimally small. And if the interval is infinitesimally small, the average velocity becomes the instantaneous velocity, or the velocity at a specific instant in time. So instantaneous velocity is velocity at a specific instant in time. Speed again. So remember that speed and velocity are often used interchangeably. and in common. And this is a mistake when we're talking about speed and velocity for physics. However, speed, as we have established, is a scalar, and velocity is a vector quantity. With that in mind, we can say that the magnitude of instantaneous velocity is instantaneous speed, because average speed is the distance traveled divided by the elapsed time. Average speed and average velocity, however, are not the same. So instantaneous velocity and instantaneous speed are the same quantity, but average speed and average velocity are not the same. Average speed. So the distance traveled can be greater than the displacement. So the distance traveled, so that is when we are calculating, distance traveled would be when we are calculating for average speed. Where average velocity, we would be using displacement, and that's what we use to calculate average velocity. And as we saw in our airplane diagram earlier, average velocity or the displacement doesn't really tell us the total distance traveled by that passenger. So the average speed can be greater than the average velocity. So let's take these examples. You drive to the store 6 kilometers away and back to your house in a half hour. So that is a half hour is 0.5 of an hour. That is 30 minutes. Calculate your average speed. So remember that your average speed is your total distance. So we went 6 kilometers to the store and 6 kilometers back. So our total distance would be 12 kilometers. So we went 12 kilometers in a half hour. Go ahead and calculate your average speed. Now, take the same situation that you drove to the store 6 kilometers away, and you return from the store 6 kilometers back to your house, and calculate your average velocity. And remember that we are not using the distance traveled to calculate our average velocity. We are using our displacement. And go ahead and think about that and calculate that. Now, explain the difference and why. Explain the difference between these two values and what caused them to be different, and explain why. So, distance, speed, another way to distance, speed, velocity versus time graph. So another way to visualize motion is using a position graph. We can take our trip to the store and visualize it on a plot. So here we have a position versus time graph, And you can see here that our position, we started at our house. So let's say this is our house. It's not a great house, but here. This is our house, and we went to the store. And then we returned to our house. So we can see that over time, our position, it changed, and then we went back to where we started over that course of a half hour. We can also do the same for velocity versus time. Velocity versus time. So this plot is a little bit different. Over here is our velocity, and down here we have a time, but our time scale is over here. So this is a tenth of an hour, 2/10 of an hour, 3/10 of an hour, 4/10 of an hour, and that would be a half of an hour, or 5/10 of an hour. So now our velocity, from our house to the store was constant because it was in one direction, and we went 6 kilometers in a half hour. So that would give us a velocity of 12 kilometers per hour to the store. So here we arrive to the store having traveled 12 kilometers per hour in that direction. Then this line where there is no change in velocity, is the period of time where we are at the store. And then the reason this point moves back to, or down to the negative axis is that, remember, since we went in this direction, which is a positive direction, we are now going from the store back to our house, and this is in the negative direction. So during this time period from here to here, we went in the negative direction back to our house. So we ended up back in the position we started from, and we traveled at 12 kilometers in the negative direction. So our average velocity over this time period would be 0. It's 0 because using displacement to calculate average velocity over this time period, we didn't technically move using the formula, even though we did, but since we went from the same initial position that was our final position during that time interval, our average velocity is 0. Okay, and here we have a distance speed, or a speed versus time graph. We have a speed versus time graph. So this is again our trip from our house to the store and back to our house. And here it shows that our average speed during that interval was 12 kilometers per hour. And that's because we are considering the total distance traveled during this time interval. That is to the store and from the store back to our house. So here we have a speed versus time graph. So now let's go ahead and check your understanding. A commuter train travels to Baltimore, from Baltimore to Washington, D.C. and back in 1 hour and 45 minutes. The distance between the two stations is approximately 40 miles. Go ahead and calculate the average velocity of the train. Now, go ahead and calculate the average speed in meters per second. So remember our conversion factor that we have 5,280 feet in 1 mile and 3.28 feet in 1 meter. So calculate average speed now using our quantities up here and our conversion factors here. And then I'd like you to draw a position versus time graph, a velocity versus time graph, and a speed versus time graph for the commuter train in your notebooks from Baltimore to Washington.